In this video, we're going to discuss how to integrate functions of several variables, and we'll focus on integrating functions of two variables. We've got the main theme for setting up a definite integral or defining a definite integral, and we're going to see this replay itself in the next few weeks for double integrals, triple integrals, and then later on for line integrals and surface integrals. But the idea and the steps for setting up or defining a definite integral is to take the region you're talking about integrating over and cut it up into a large number of pieces. I'm going to call that n here for discussion for now. All right, and then for each one of those pieces, we're going to pick a point out of that, plug it into the function f, and then multiply it by the size of the piece under consideration. And we're going to see for double integrals versus triple versus some line integrals and surface integrals that size could mean different things. Take those results then, sum them up over all the pieces, and take the limit as the size of each piece, or in general the pieces shrink to 0, or that is, you're increasing your partition size. Alright, now we've seen this for functions of one variable in Calculus 1, and I want to review that before we go on to functions in Calculus 3 here, functions of two variables. Okay, so just as a reminder, how does this go in the single variable case? Alright, our usual definite integral for scalar functions. In this case, we're talking about an interval on the number line, so we have an interval on the x-axis, say, and we're talking about our function being defined between, say, a and b. There we cut up or partition the interval into lots and lots of what we call subintervals, and say we use n subintervals. Then we define delta x to be the width, assuming we're talking about a constant subinterval width all the way across. For each one of the individual subintervals, we're going to pick a point out from there, right? Call that special point x sub I star, if that's the ith interval, say, and then plug that into the value into the function, plug that input into the function, and multiply it by the subinterval width, which is delta x. Adding those all up, taking the limit as n increases, gives us our definition for the definite integral that is familiar from Calculus 1. Alright, and we're seeing that down below here. Alright, that's how we define a definite integral. And that definition is important for verifying various properties with integrals. Alright, because we know certain properties with limits, such as that a limit of a sum is the sum of the limits, and constant factors come along for the ride for limits. Those properties carry over to integrals. We can integrate term by term, and constant factors come along for the ride. And that's an important reason why we need to discuss that limit definition there. All right, even though when we go to actually compute definite integrals, as I have toward the bottom here, we rarely likely used that in Calculus 1 for actually evaluating a definite integral. We more relied on the fundamental theorem of calculus, or maybe an area interpretation. Alright, so just remember how we usually compute those definite integrals is find an antiderivative and then plug in the upper limit of integration and subtract what we get by plugging in the lower limit of integration into that antiderivative. Okay, and we also know the geometric interpretation for definite integrals. Alright, for scalar functions, it's the area under the curve. Alright, I just want to show a quick animation in Maple before we go on to two variable functions. Alright, so I've got a couple of functions plotted here, and when we increase the number of partitions used, so now we're talking about going from, say, maybe 4 to 8 and keep on increasing, or in this case it's 20, I guess, actually now, and 40, starting out with 5, and then it's going up to 10, and then 20. Alright, notice what we're seeing there is that integral from 0 to 5, alright, is getting closer to the exact value. If you can see, this number is getting closer and closer to the exact value, which I think is 69.3, or somewhere around there. 69 1/3, I think, is what this integral comes out to, but it's more about the limiting process. Alright, so we see as we increase n, alright, as n is getting bigger and bigger, it's going to be approaching infinity, the approximate area under the curve, which is the sum of the areas of these rectangles, is going to get closer and closer to the exact area. Alright, and this is the example that we had in the handout. If we increase the number of partition points, and notice our function can be above or below, the x-axis. Again, as we increase via that limiting process, we get the exact answer. All right, so again, the limit definition is important. All right, and that's part of the graphical interpretation of it, was area under the curve. It's the net signed area under the curve, or between the graph of the function f and the interval AB on the x-axis. All right, now we're going to move on to functions of two variables. All right, and we want to ask this question: how do we generalize this? If we got a function f of x, y, a function of two variables, and we're going to start out with the simplest possible case. Things are more complicated, as we've seen with limits and derivatives, partial derivatives and directional derivatives and such, for functions of two variables and beyond. We're going to start out with the simplest possible case, where we're integrating a function restricted to a rectangle. And you might see it sometimes written with this set builder notation. We might also see this Cartesian product of these two intervals. So the interval AB cross the interval CD. What we're meaning is, like in this picture down below here, you're taking the interval from A to B on the, all the X has got to be between A to B on the x-axis, and Y has got to be between C and D on the vertical axis there. That determines that rectangle. Alright, so we're going to stay with the main theme of how we set up and define a definite integral. We're going to cut up the region into smaller subregions, in this case smaller pieces. The pieces we're going to use here are going to be subrectangles. If we partition the x-axis and the y-axis, that naturally gives us a lattice of points, and therefore that gives us some corresponding subrectangles. For each one of those, we're going to pick up, for each subrectangle, we're going to pick a point out of there and call that, say, x sub I star and y sub j star. Plug that into the function and multiply it by the size of that corresponding piece, that corresponding subrectangle. What is that going to be? That's going to be the area of that rectangle. All right. Now the area of that rectangle is just going to be, denoted this way, delta A sub ij, and A represents area, but we can simply compute that by doing the product of delta x times delta y. All right, keep that in mind, because when we start evaluating double integrals, we're going to see either dx dy or dy dx. All right, so then we plug that point into our function, okay, and then multiply it by the size of that piece, which is that corresponding area. Add them all up, sum them all up over all subrectangles I and j, and take the limits as the number of partition points on the x-axis and the y-axis both go to infinity. That leads us to, this is a nice picture from OpenStax, this leads us to the limit definition for the double integral. All right, the integral of a function of two variables over a rectangle, R, capital R. It's a limit, and we've got a double sum inside of there, and then again, that double sum is making us think double integral. That is even a more difficult expression to work with than the single variable case. All right, so let's take a look at what that looks like, though, before we go on. Over in Maple, geometrically, what are we looking at? Okay, so here's what we're going to be looking at here. Looking at this rectangle in the xy plane from 0 to 2, and from y going from 0 to 1. If we increase the number of partitions, we get many more and more subrectangles inside of our region R that we're integrating over. All right, now what I'm be looking at in this worksheet is this function 10 minus x squared minus y squared. That graph is given here. All right, and the graph of that is the top here. That's the surface. That's the graph of the function f. When we restrict it to the rectangle in the xy plane from 0 to 2 in the, along the x-axis, and 0 to 1 along y. There's that graph. All right, and we can see kind of what's going to be happening here. We're looking at that solid volume underneath that graph. All right, now this next picture gives a visualization of the individual things that we have inside the Riemann sum defining the definite integral. So let's just go back to that for a minute. Inside of there we have a sum of a number of things, and what do we have? What are we summing up? It's the product of the function value at the specified point times the area. All right, and that area times that number, that height, this is going to be an area times a height. Okay, that is going to correspond to the volume of one of these boxes. All right, so if we look over top of this, I'm just going to rotate this down. We're looking at over top of that region, we're splitting it up into many pieces. That product we can visualize as the volume of that 3D box. Now, what happens when we increase the number of partition points? We're going to get more and more of these boxes, and we're adding up the sums of the volumes of all those boxes, or also called parallel pipe beds. And as we increase that, we can see this limiting process happening here. We're going to get closer and closer to the exact volume in this case. So what are we doing with that Riemann sum? That limiting process, it's going to yield for us a volume if we're talking about a function whose graph is above the xy plane. Okay, so that volume is getting closer and closer to this exact volume that we have pictured up above. Okay, going back over to the notes here. A couple of remarks now going forward. This definition up here, as we said a minute ago, very difficult to work with, all right, but it's very difficult to compute double integrals with that, and we'll discuss how we're going to be doing that in just a moment. But we need this definition. It's an important one to still come up with the same properties of definite integrals that we're used to. And the main two that I have listed here, and this is taken from the OpenStax book, is that the integral, the double integral of a sum, is going to be the sum of the double integrals. We can integrate term by term. And then the second one is that we can pull constant factors outside of an integral. So we've got a constant factor that comes along for the ride in the sense that that constant factor can be pulled outside in front and brought along. We just mentioned a minute ago that for positive functions, the double integral will give you the volume under the graph above that rectangle. Okay, in general, it will be the net signed volume. All right, how do we extend that definition for regions that are non-rectangular, like we have pictured here? We're still going to lay a grid over top of it, except we're just going to consider the rectangles that lie completely on the inside of the region. All right, as we increase the grid mesh, we use more and more points, and then our mesh gets finer and finer. We'll have more and more subrectangles inside the curved region. All right, there's a couple types of errors that we can get, of course, from that. We won't focus as much on these in this video, but let's talk about how we're going to actually be computing these double integrals. All right, so this is an important result. It's called Fubini's theorem. If we have a continuous function over a rectangle, then we can do that in one of two ways by computing an associated iterated integral. So we can do an iterated integral, either a dy dx integral, meaning integrating with respect to y first and then with respect to x, or vice versa, integrating with respect to x and then y. All right, in subsequent videos, we're going to be seeing examples of how to evaluate iterated integrals like that. But again, just notice the difference between that. Over here, we have dA from the limit definition. That stands for the area element. All right, and now this is a special result that we can take that double integral, which is hard to define, and compute it via an iterated integral. And that's going to be a simpler task for us. All right, just to visualize why that is correct, what I've got here is a quick picture here in Maple. So here's the same function we were working with before. And the idea behind Fubini's theorem is that we can cut this up and partition this into slabs. And those slabs are going to, as we cut up the x-axis or the y-axis finer and finer, going to give us an approximation to that volume. All right, now, why does that give us the same result as the iterated integral? Well, if we think about fixing x at, say, 1/2, I've done that, and letting y vary, then that gives us a function restricted to a curve. If we look at what's underneath that curve, that's an area. How do we compute that area? We do that with an integral. All right, so that's going to be that specified integral. All right, and then if we fatten that up a little bit by sliding it along the x-axis, we get one of the slabs. So that just gives an idea of why Fubini's theorem is true.